problem 1044, longest duplicate substring. And this problem is really easy to understand. As we can see that we just need to check the duplicate substring, but it must also be the longest. So for example, ANA from here and another ANA from here, so it is the longest. Yeah. So first of all, I've used the z function to solve the problem, but that is not possible. If I use the z function, it is basically string matching. Yeah. So I have to check. I have to use the O(n) square time. So for example, I'm gonna use this string, and then I'm gonna start using ANA, NA, and here I find the result by using the z function. Yeah, because z function is basically for checking the maximum prefix. So if it is here, it is 3, so I can get the result. But it will be time limited exceeded because it is O(n) square. Yeah, let me just copy my z function code to explain a little bit why it didn't work. Yeah. Here I will not explain everything about the z function. I just want to explain the z function didn't work. So this is the z function template. We prepare a template and then we're gonna use a brute force to check one by one. So first of all, from the index 0, we're gonna get a z function, get a result array, and then we're gonna check the maximum of the z function. Yeah, if this maximum is less than the result, so we're gonna update the result. So this is from si, sliced to until to the max. I get the result. Yeah, but it didn't work for all the testing cases. If I run it, you're gonna see what's gonna happen. Yeah, z function can solve the prefix problems. Yeah, it's gonna be O(n) time for checking the prefix. But if it is the string is very long, this is the O(n) square time complexity, it will not work. Yeah, if I delete some testing cases, let's see what's gonna happen. Yeah, as you can see, it works, but it cannot pass for all the testing cases. It can only pass some of them. Yeah, I just draw a time limited exceeded situations, and then we're gonna try to use some other ways to solve the problem. Yeah. So as you can see, it only passed more than 50 testing cases. Yeah, actually for such problem, we can use a binary search to solve the problem. Yeah. So for example, if we have a string like banana, and what's gonna happen? By using binary search, we can just guess, because this kind of search is this kind of the property of the duplicate substring is monotonic. Yeah, if it is monotonic, we can always use a binary search to guess the answer. Yeah, this means if there is only one character, yeah, we're gonna check what's gonna happen if there's only one character. Is there a duplicate? Yes, there is. The duplicate will be if one character, so the duplicate will be like a. So what if there are two characters? Yeah, so the duplicate will be like an and NA. Yeah, what if there are three characters? Is there a duplicate? Yes, there is ANA. Yeah, because there is another ANA, so it is a duplicate. But NAN it is not, and ANA it is a duplicate, right? Yeah. So what about there are four characters? Is there a duplicate? No. Yeah, we're gonna use ANAN, but there's only one ANAN. There's no two ANAN. Yeah. So this is exactly the monotonic properties. So this means we can use a binary search. But if we use binary search, what's gonna happen? For example, if we guess, so for the banana, if we guess the length of the string is 3, we're gonna find the duplicate for the 3 for the length of the substring, which is 3. Is that possible? We can use a hash table. If we use a hash table, for the hash table, actually it is not O(n) time. So the hash table, the time complexity would be O(n) times L. So L is the longest length of the string. So this L can be n. So it means this is O(n) square. And we're gonna use a binary search times log k, for example. Yeah, definitely this time complexity is even more than the z function. Yeah, you see from here, z function is basically O(n) square. It is not possible. So if we use the binary search with the hash table, it is n squared times log k. Definitely it is not possible. So this means we're going to use some clever ways to solve the problem. So this comes to the rolling hash. Yeah, let's first analyze what is a rolling hash. The rolling hash algorithm is also called Robin Cup algorithm. So for this algorithm, actually it used the mathematics skill to solve the hash conflict. Normally for a hash, there might be a hash conflict, but here we're going to use some mathematics skill to solve the hash conflict. But we need to understand how it is actually calculated. So for example, if the length of the string is 4, yeah, we're going to first check this BA, NA. Yeah, so for this BA, NA, what's going to happen? So we're going to use some properties. So for example, B, we're going to use this B times, we're going to use a fixed number like 26 to the power of, yeah, you can use other numbers, it is also okay. Here I just use a 26. This is my design. Yeah, I designed it to be a 26 as my base. Yeah, if it is a binary bit, I can use a 2, but here for this characters, there will be 26 characters, so I design a 26 as my base case. So if it is a B, it's going to be 26 to the power of 3 and plus this A times 26 to the power of 2 and plus another n, yeah, and times 26 to the power of 1 and plus the last one, A times 26 to the power of 0. Yeah, so this is my definition of the rolling hash. Yeah, so for here, so for the value, I'm gonna design a hash value as 8. So this value I'm gonna design it as my hash value. So this is the low bit and the BA is the highest bit. So this is similar like the binary numbers, but here it is like 26 possible result. So from A it is 26 to the power of 0 and this 1 and this A 2 and this B gonna be 3. Yeah, so if this gonna be rolling to another window, so as you can see, it is similar to the sliding window problem. If it is rolling to another window, for this one, it's gonna be AN. Yeah. So what's gonna happen if it is rolling to AN? Yeah. Let's check the result. So for the AN here, I'm gonna make it H2. So this means after sliding to AN, this B will be deleted. Yeah. So what's left behind? It is this one. So let me just copy. So actually this one should times 26. Yeah, because as you can see, all the positions have been shifted one place to the right, and we also introduced another character which is n. So we need to plus n times 26 to the power of 0. Yeah. So after updating, so here gonna be the power of 1, and here gonna be the power of 2, and here gonna be power of 3. Here I just need to delete this 26. Yeah, so this is after updating of the sliding window. As you can see, this is just O one time. It is not ON or OK or yeah or some other time. It is just O one time. We just need to prepare a sliding window first. Yeah, for preparing the sliding window, it is like ON time if the window size is too long. But after preparing for the window, we just need to use O1 time to update each of the element. If it is added with n, if it is added another character, for example m or other character. Yeah. So for the next one, it will be NA. Yeah, we just need to use O1 time for updating the result. So this is the time complexity becomes ON times log k, and this is why it can pass. Yeah. Now let me start coding for the loading hash. Yeah. As I said, I'm gonna prepare binary search. So L R and result. So the L would be starting from 0, and R it would be length of the string, minus 1, because we are calculating the duplicate. For example, this length is n, and what is the maximum result? It's gonna be like n minus 1. Yeah, so I'm gonna use n minus 1. Yeah, because if this is n, it must have a duplicate, so the longest should be n minus 1. So here is the length of s minus 1, and the result I set it as 0. And then I'm gonna prepare the boundary template. Yeah, so m should be equal to L plus n divided by 2. So if check m, so this is just my template for the boundary search. I'm gonna record the result. I just write it like that, and after that I will update it. It's according to how I'm gonna write my rolling hash function. Yeah, and now if this m, for example, if this m is for example, if this m is small, we want to have a bigger value. Yeah, this m is true. Here, this check m means this m is true. I'm gonna guess a bigger value. If I were to guess a bigger value, so L should be updated to n plus 1. Otherwise, if it is false, I need to reduce it, so it's gonna be a smaller value, so R should be equal to m minus 1. Finally, I'm gonna return something. Yeah, currently I'm gonna return a result as my template, and later on I'm gonna change this result, because definitely it is not a number. Yeah, it will be a string. Yeah, I will change it to string. Yeah. Now let's just go to the check function. Inside of the check function, I'm gonna give a threshold. Yeah, but I want to let this threshold to L as my window size. Yeah. So out of the check function, I'm gonna prepare the hash. Yeah, I'm gonna call it rolling hash parameters. So the parameters, I'm gonna prepare a mod. Yeah, I'm gonna prepare a mod. I'm gonna prepare a power p as 26, and my mod would be equal to let's say 10 to the power of 32 minus 1. So this is always dependent on my design. So I designed it like that. If it is not possible, I'm gonna change it, because rolling hash is not 100% right. Maybe it is a 99.999% right, but definitely it is not 100. But yeah, if this is like the precision, if the precision is just like yeah, let's say if the precision is just like 99.999, and yeah, definitely there will be an infinite of 9% right. We're gonna say this rolling hash is right. Yeah, it is not 100%, but yeah, it is basically it's equal to 100%. Yeah, it's not exact, but it's nearly to 100%. We can say it like that. Yeah, so this is my definition. I'm gonna define another power and power. This will be a big power. It's gonna be 26. I'm gonna explain. Yeah, so this one I think we should understand. This is a definition of the power. I'm gonna use 26, and the definition of the mod. And here, this power and power, I'm gonna use 26 times L. L is the window size. Yeah, I'm gonna use this variable later. Yeah, here I just prepare for it, and I'm gonna use a mod, because this is gonna be a really big number. I don't know the window size, but definitely it's gonna be a big number, so I'm gonna modular the mod. So this is some preparation, and now I'm gonna init the window, and after that I'm gonna use the sliding window. Yeah, there will be 2 steps. So how to init the window? We just need to check the first L characters. So for example, if we use this banana, if the window size is 3, yeah, what are we gonna do? So L equal to 3 here. L should be equal to 3. Yeah, we just need to enumerate. Yeah, so for I, Yeah, but as you can see, this is a string, but actually I don't want it to be a string. I don't want to have a string. I want to have always be integers, because integers is used for calculations for the loading heads. Now I'm gonna turn it to integers. So how can I turn it? It's gonna be odd of a character minus odd a. Yeah, I'm gonna turn it to integers. So for example, for a it will be 0, for b it will be 1, and for z it will be 25. Yeah, it doesn't matter. I just turn it to integers like this. This is also dependent on my design of the algorithm. Yeah. So for C in S, so we're gonna turn the string to an integer array because we're gonna use it for the loading heads calculation. So for in in enumerate big S. Yeah. Now we're gonna check the hash value. So here I'm gonna prepare a hash value. Yeah, let me put it here. I'm gonna prepare a hash value is 0. Yeah. So for the hash value, I'm gonna update, prepare the hash value. So here will be some calculations. Yeah, I explained it before, but here I just need to, for example, if this L is 3, I need to update the hash values. Yeah. So it will be something modular the mod. Yeah. And inside, it will be 8 times p minus plus n. Yeah. Let's just check one by one. So for example, L is 3, we're gonna check BAN. Yeah. If we put B inside, what's gonna happen? Because this B is just a number, it doesn't matter. Yeah. So this 8 is 0, 8 times P is 0, so we're gonna put the first character B inside. Yeah, now it's equal to B. B modular mod is still B. And now we're gonna put A inside. So for this B, it will be updated to B times 26, B times P, and plus this A. So it means this formula should be right. Yeah. So this is basically the preparation for the initialization for the window. Now we're gonna start the sliding window. Yeah. So for here I didn't use this I. Yeah, I think it is okay. Yeah, even though yeah, let me check. Do I need to use it? I don't need to use this I. Yeah, I don't need to use it. It is okay. And now let's just check another one. So here I'm gonna use R. So for R in yeah, because this is the right side. So here I'm gonna use the right pointer. So for R in enumerate. So here I'm gonna start from the else characters. Yeah, because this is the sliding window. After this one, BAN, I'm gonna start with this A. Actually, it is ANA, so I'm gonna start with this A for calculating. And the index, sliding index would be also L. Yeah. Now I'm gonna update it. So it's gonna be something modular a mod. Yeah, modular mod. But for this calculation, we need to do some tricks. Yeah, so this is 8 is the previous value. So the 8 should times p. So this means all my previous result times 26. But that is too big. It would be minus the first value, minus the biggest value. So this biggest value would be as yeah, let me think, R minus L. So for example, if this R, if the L is 3, so this R is 3, and the length is 3, so it means this is 0, S0. So S0 means it is this character B. So for this character B, it should times this pp. So this means yeah, 10 to the power of 26 to the power of 3. Yeah, 26 to, yeah, this is a power to the power of L. Yeah, this is why I'm gonna use this variable. Now I think it's explained. I'm gonna use 26 times to the power of L modulo the mod, and yeah, I need to minus the biggest value. So for example, from BAN, I slide it to ANA. Yeah, if I slide it to that, I need to minus this B, and this value is exactly the B, and I need to plus the last value. It is N. Yeah. Now this value 8 is updated. Yeah. And also for here, after calculating this its value, I need to put it inside a visited set. Yeah. Visited. Yeah. Let me check. Should be, yeah. I just initialize it and put it inside the 8 hash value. Now I'm going to check this hash value, this 8. Yeah. So if this 8 inside the visited set, what I'm gonna do? I'm gonna return something. Here is I'm gonna return a true, but I will not return true directly because I'm going to calculate the string. It's not a character. It's not 3. It is a character string like ANA. Yeah. So this means I'm gonna return the first index of the string. So what is the first index? Let me check. Yeah. So the first index is gonna be R minus L plus 1, and the length of the string is just L. Yeah, let me just double check if it is okay. Yeah, let's just check this one, ANA. Yeah, now this is ANA, and after we get this this ANA, what's gonna happen? Yeah, if it is inside, yeah, let me just check 3 characters. First 3 characters we have BAN, and the next 3 characters we have ANA. And for here, if this ANA is just inside, yeah, what's gonna happen? Yeah, if ANA is inside, I'm gonna return this index. So the index of this A is 1. Yeah, so here, this R, it is 3 minus L, 3 plus 1, it is 1. So this means my index is right. Yeah. So for here, you just need to use examples to output the right index. So this basically means true for the check function, but I didn't return true. Yeah. Then, if it is not, visited should add the hash value, and after that, if it is not true, I'm gonna return a false. So this is the entire code for the binary search with zoning hash. Yeah, it is not exactly right, but at least it can pass for some testing cases. I just need to check if my code is totally right. If it is not, I have to debug to find what is wrong with it. Yeah, I didn't make it right because my result is just M. Yeah. Yeah, let's just wait for a few seconds. Yeah, this is too long, definitely, but I need to just run it to check. At least it can pass. At least I can output some result. Yeah. Now I output a 0 for the first one. Yeah, I should output a 1. I should output a 3, but it is 0. I think the length should be yeah. This is just because I return M. Yeah, it should be 3 normally. Yeah, and this is 0. The length is 0, and the last one BAN should also be 3. Yeah, it means something wrong with my code. I have to check it. Yeah, it's really difficult to check. Yeah, this 8 is this value, and if it is inverted, yeah, but anyway, I'm gonna return the right result, right? I'm gonna result should equal to tag m. Yeah, it's not m. Anyway, I'm gonna return the right result to tag what's gonna happen. So the index and L should be equal to result, and my final result would be S with index to index plus L. Yeah. Let me just check what's gonna happen for the result. Cannot unpack. This tag if I put it inside, if it is true, yeah, I cannot unpack. Yeah, let me just print out the result to see what's gonna happen. Yeah, if this is true, I'm gonna return a tuple, but I can't unpack. Yeah, let me just make a comment about it. Just return empty string. Yeah, this is a string. Yeah, what did I return? I return an empty string. Yeah, but basically the tag function didn't work. Yeah, because I didn't print out anything. Yeah, this means my tag function didn't work. Yeah, here prepared the visited set. If this is inside, I'm gonna return a tuple. I don't know why it didn't work. Yeah, let me check the binary search. Yeah, if this m works, let me print out the m from here. Here gonna be the tag. Yeah, it is a 2-1. It never runs the tag function. Yeah, this is a really interesting part. Yeah, it didn't. It means the tag function is always false. I never have a return. Yeah, definitely this gonna be something wrong with my tag function. Yeah, because of, normally for the binary search I should not make a mistake. So if tag, I'm gonna guess a bigger value. Otherwise, I'm gonna guess a smaller value. Yeah. So for the rolling heads part, I have to check my formula. Yeah. So I designed a mod and p and s. Yeah. I just need to check this L threshold. This is and 8 for I enumerate s, and this 8 should 8 times p plus n. Yeah, I forget about I'm not sure. No. Yeah, modular the mod for each one of them, and put it inside the weighted set. and another 8 is 8 times p minus this one, r minus l. Yeah, here I use to the power of pp. It's not to the power of pp. It is a times p and p. Yeah, this is a silly mistake. This is really a silly mistake. It is a yeah, because this p is 26 to the power of l, and this is just needed to times the result. Yeah. Now let me try. Yes, it's still a mistake. It's not like that. Yeah, I can also change this to p. It doesn't matter because it is 26. Now I'm enumerated from this L, and yeah, let me just check the code I submitted a few minutes ago. Why it didn't work right now, I have to check with it. Yeah, I guess it must be my formula is not right. Let me just check the formula. This is h times p plus n modular the mod, and here this h times p minus s times pp plus n. Yeah, if it's inverted, I'm gonna return r minus l plus 1, and inverted should add. Yeah, it's exactly the same. I don't know why it is wrong. Yeah, it's gonna be difficult to debug. Yeah, definitely I don't know what is wrong with it. Yeah, I think it's exactly the same. I didn't find any difference. Yeah, I just prepared a mod. Yeah, let me put it to mod plus 1. I don't think that is the reason for it. It doesn't matter. Yeah, this as odd C, odd A for C in S. I also prepared for that. And the check function, I prepared L and this 8 and this pp, p to the power of L modular the mod for in. Yeah, here I did something wrong. It's really from this S string. Yeah, it is not from S. It is from SL. Yeah, because the window size is 3, I put a window size of string S. Definitely it is wrong. This is something I didn't find. Yeah, even I corrected it, I still get it wrong. This is gonna be really interesting. Yeah, you know, before S definitely wrong, it should be to L. Yeah. Now let me yeah, just to run it to check. Yeah, because I didn't return anything else, so it should be wrong. But I would to check the result. It seems the result is okay. Yeah, I just need to uncomment those lines and delete the printout just to make everything looks clear enough. Yeah. Now let me just run it. Yeah, as you can see, it works. This is a silly mistake I made because I didn't think carefully for this kind of the window size. It is L. Yeah. Now we finished the part of the algorithm. Basically, it is okay, but we need to consider the loading has conflict. Let me just submit it to check what's gonna happen if I just submit it. As you can see, we got a wrong result. Yeah, this is because of the loading has issues. It's not about my coding is wrong. It's just because of the properties of the loading has. As you can see, for the testing case 64, it didn't work. Yeah, maybe I can change some numbers for the mod. So for example, I'm gonna change 32 to 35 plus a 7. Let's just check the result. Now let me submit it. As you can see, this testing case works. Yeah, and it also works after submitting. But zoning has is not about just guess. We are not about to guess the mod. We just need to make sure it works. We don't need to submit it and check if it works. Yeah, but how can we correct that? Yeah, we're gonna redesign of the mod of the zoning has. So 2 to the power of 32 gonna be -1. Yeah, from the beginning. I just needed to check. Yeah, as you can see, 2 to the power of 32 -1, it passed for this testing case, but it didn't pass for all the testing case. Yeah, we just needed to redesign this zoning has algorithm. Yeah, this testing case didn't work, but up to now it is still okay. This means we can change something. Yeah, we needed to add some mod if it didn't work. For example, currently it may be 99%. 99% of the probability it is right, but it's not 100. In order to make it 99.99% right, we need to add another mod. Yeah, so we're gonna add another mod. So this mod would be 2 to the power of 32 plus 1. Yeah, now we just need to add all the mod 2 to our result. Yeah, it's gonna be just easy. And this pp modular, yeah, this here, because here we used a mod, so we're gonna just copy the code and prepare another one. So this one gonna be pp2 and with mod 2. Yeah, I'm gonna put the 2 mod inside the weighted set. So in this case, there is a high probability that the testing case can pass. We can pass all the testing cases. And here I'm gonna update it to h2 because here I have another mod. So here h2 would be h2 times p plus n modular mod 2. So similarly here I'm gonna prepare h2 equal to 0 from the beginning. And now I need to update this line. Yeah, I just needed to update it to h2. And for the weighted set, I needed to put the h and h2 inside. Because if I put a tuple inside, there will be a less probability of the hash conflict. Now I will have no hash conflict. Yeah. Now from here, I'm gonna update it with h2. This is gonna be ps. This is gonna be pp2 modular 2. Yeah. Now I'm gonna check if this tuple of h and h2 inside the weighted set. I'm gonna return that. Otherwise, I'm gonna add a tuple inside h and h2. Yeah. If I didn't find a true, I'm gonna return a false. Yeah. Now let me run it to check if everything is okay. As you can see, now it passed all the testing cases. Now let me submit it to check if it can pass all the testing cases. As you can see, it now passed all the testing cases and it should be 100%. It should be nearly to 100% right. Yeah, because we prepared 2 modular cases and we put the weighted set with 2 values. Yeah, if one value, the probability is 99%, but if we have 2 values, the probability will like 99.99%. Yeah, so that is why it can pass. Let me submit it again to prove it should always work now. Yeah, as you can see, it works, although it is a little bit slower, but it is totally right. Yeah, because zoning hash is not like KMP or Z function. For KMP and Z function, it is 100% right. It is a stable algorithm. But for zoning hash, it is not stable. So we have to use some tricks to let it pass for all the testing cases. So this is the entire code for today. It is a little bit long, but I think it worth practicing for this kind of a problem. Thank you for watching. See you next time.